So today we will do Stokes Theorem, and this will be our last big topic in this chapter. Stokes Theorem. We need to remind you of some basic stuff that we did in this chapter, and we can say that after finishing this chapter, if anyone asks you what are the biggest topics that you did in this chapter, your answer would be, it has to be a Green's theorem, the divergence theorem. And we need to say that the divergence theorem is sometimes called Gauss theorem. Okay, we didn't mention this before. And now the last big thing is Stokes theorem. Remember, what was Green's theorem? What was the divergent? And now what is the last theorem? Green's theorem was about if you have a curve integral, you can do it using a double integral. And of course, you can look at it the other way, although it's very rare to look at it the other way. But sometimes from the theoretical point of view, this is important. We looked at this, for example, in one case when we found the area of a region bounded by a closed curve using curve integral. We looked at it this way. Then the other theorem, the divergence theorem, was about converting a surface integral into a triple integral. So now what is Stokes theorem? Stokes theorem, this new title, is about a relation between curve integrals and surface integrals. So it's like curve integral with surface integral. This is what Stokes theorem is about. So let me write the statement of the theorem first. And then we emphasize the orientation, then we see some examples. So the theorem says, remember, we mentioned this many times. In this chapter, we're dealing with smooth functions, smooth curves, smooth surfaces. Everything is smooth. What do we mean by smooth? We have continuity, we have partial derivatives, we can have some cusps, and remember when we say a cusp, that means a point where we have a problem. For example, if you have a cone, this is called a cusp. At this point, the surface is not smooth. Or if we're dealing with this function, the function is not smooth. But as one point, we don't care. If you have 2 points, 3 points, finitely many points, we don't care at all. So in this chapter, we're dealing with smooth functions, smooth curves, smooth surfaces. So I'm not going to mention this again in the statement of the theorem. So the theorem says, if you have a surface, let us be a surface in R3, and I like to call the boundary curve with an opening curve C, then. So I want to explain the meaning. What do I mean by the opening curve C? Remember, in the divergence theorem, we need to make everything clear, because now it's time. You will see in Stokes theorem, it's time for a little bit of confusion. So in the divergence theorem, if you remember, the surface S has to be closed. It must be. If it's not closed, you can't apply the divergence theorem. In Green's theorem, the curve C must be closed. You can't apply Green's theorem without having a closed curve. Now, the first difference in Stokes theorem, the surface, I'm writing it, surface S is not closed. It has to be not a closed surface. I'm not saying open, because open and closed in mathematics, they have different meanings. So the surface S is not closed. So now what do you mean by not closed? Not closed, like if you're dealing with a full sphere, A full sphere, that's a closed surface. But if you take a hemisphere like this, only the hemisphere, half of the sphere, it is an open surface. For example, if you look at the cone, without its top, it is an open surface. If you look at the cylinder, without its top, without its bottom, it is an open surface. Even if you look at the cylinder with its bottom included, for example, it's still an open surface. So I'm going to shade the opening by green, the green color. So this is where the surface is open. This is the region where the surface is open. Now, in the statement of the theorem, I'm saying, let us be a surface with opening curve C. So what do we mean by the opening curve? You look at your surface. You say, okay, my surface is open from this area. So in this case, this is where your surface is open. This is called the opening curve C. This is the opening curve C. This is the opening curve C. For example, if you're dealing with an open cylinder from both sides, from the top, from the bottom, so imagine this is your cylinder, this is your surface. In this case, you will have two openings. You have an opening from here, you have an opening from here, from the top, from the bottom. In this case, what is your opening curve? From the top, you have this, from the bottom, you have this. So in this case, you will have two opening curves. So this is the first thing. This is the meaning of the opening curve. Now, Stokes theorem relates the surface integral over this surface with the curve integral over its opening curve. So what is the theorem saying? Then if you compute the curve integral of the function, and remember, the curve integral is integral over C f dot dr, it will be equal to the surface integral of what? Not f, of curl f dot n dA. So if you integrate the function over the opening curve, it will be equal to the surface integral of the curl over that surface. It's a little bit confusing, but this is the statement. So it's about a relation between curve integral and surface integral. And what is C? It is as explained by these red curves. So this is the statement of the theorem. Of course, at this point, and I'm sure most of you started asking about what? About the orientation. So what is the orientation in Stokes theorem? For example, imagine your surface was just a disk. So for example, if you look at x squared plus y squared less than or equal to 1 at any level, for example, when z is equal to 0. So this is this disk. Now this disk, it is by itself an open surface, and this is the opening curve. This is the opening curve. So now we're saying that if you integrate over the curve, it will be equal to the integral of the curl over the surface. So you integrate over this curve C, it's the same as integrating the curl over the surface S. So the question is, what is the orientation of the curve and what's the orientation of the surface that guarantee together this equation? Because remember, you have two orientations for C, you have two orientations for S. So changing the orientation gives you an extra negative sign. For example, if you integrate over this orientation, the function for the curve, if you integrate the function over this curve in this orientation, for example, you get 5. If you do it the other way, you get negative 5. The same thing for the surface. If you integrate, and remember the orientation of the surface is specified by the normal vector. So if you use this normal vector, you get 5. You use the other normal vector, you get negative 5. So which orientation do you take for each of them to guarantee this equality? So our remark about the orientation. So our orientation remark. if you look from the tip of n, what's n? N is the normal vector. N is the normal vector of the surface. So imagine you're standing, imagine you are the normal vector. You are, yes, you are the normal vector. So for example, if this is your normal vector, you are this guy. You are standing exactly here. Now imagine you are standing there and you are looking at the curve. So if you look from the tip of n to the curve, the orientation of C, the curve, must be counterclockwise. So this is the orientation we use for the normal vector and the curve C. So to make this clear, and in my opinion, I might be wrong, this is the most important thing, because otherwise we're just doing some integrals. But the most critical thing in Stokes theorem is determining the orientation of both the surface and the curve. So imagine this is your surface as a disk. So this is a disk. I don't care now what the equation is, but imagine you have a disk. So for this disk, you can have two orientations. It's either the upward normal vector or the downward normal vector. Now, let's say you are taking the upward normal vector. So if you decide to have this n, imagine you are this guy. Imagine, so this is you. This is you. You are standing, so this is you. I'm not good in drawing, but this is you, okay? And imagine you are standing here and you are looking at the curve. If you are looking at the curve this way, the curve has to be oriented counterclockwise, which means it has to be oriented that way. So this tells me that if you take the upward, in this case, if you take the upward normal vector, then the orientation of the curve has to be this way. For example, imagine you have a hemisphere like this. Now for the hemisphere, and this is my opening, so I will keep using the same colors every time just to make things consistent. Okay, so now for the surface, we know that the normal vector of the hemisphere is the extension of the radius. So this is the radius. It could be this thing, this thing, this thing, and so on. Or it could be the other way. So it could be this thing, but I don't want to draw it, but it's like, so it could be these things, right? So now, if you decide to go with this normal vector, so imagine this is your normal vector. Again, imagine you are this guy. This is you, okay? And you are looking down. So you are up there. You are looking down to the curve. This is my curve, okay? This is my curve. So now you look at this. Imagine this is a watch. Imagine this is a watch. So this is a 12, this is 3, this is 6, and so on. So you say, okay, if I look at this curve, the orientation has to be counterclockwise. If you agree, this is the counterclockwise direction. So if you choose this normal vector, you must choose this orientation for your curve. For example, let's say you have this cone like this. Okay, so for this cone, and this is on my opening, so this is my curve C. So for this cone, you can have the normal vector either this way or the other way, let's say the outward and the inward. So if you look at the outward normal vector, again, imagine you are this guy. This is you. And you look at the curve C, the red curve C, and imagine that's your watch, okay? So that's your watch. How is the orientation of that watch? So if you agree, in this case, this will be the counterclockwise orientation. Your watch will be running the other way. Maybe it's good at this stage if you really carry your watch and you just look at your watch from downward or from upward and see how the orientation is different. Again, this is quickly about the orientation of the surface, and we will see more emphasis on this through the examples. So I like to start now one example. For example, I would like to say verify Stokes theorem for the function f that's, for example, equal to 2x y cube z, and for s equals all points such that x squared plus y squared is less than or equal to 1, and for example z is equal to 0. Now what do we mean by verify? What do we mean by verify Stokes theorem? Verify Stokes theorem, we mean we want to show through this example that this identity is really true. That's it. This identity is really true. This is the Stokes theorem. So basically we need to compute two things. We need to compute the curve integral of f dot dr. Then we need to compute the surface integral of curl f dot n dA, and after doing all computations we need to show that both quantities are equal. So first, before starting the computations, what is my surface? My surface is the disk at the z equals 0 level. It is the disk, so this is my surface S. Now in this case, what is my curve? This is my curve. So what is the orientation for this disk? The orientation can be, for the normal vector of this disk, it can be upward or downward. If you imagine you are this blue guy here and you look down to the red curve, what is the orientation of the red curve? It has to be counterclockwise. It will be this way. Okay, of course, we might need, this is the x-axis, this is the y-axis, and this is the z-axis, okay? Remember, the x-y-z axis must be drawn according to the right-hand rule. So when we say the right-hand rule, that means this is the thumb, okay? Okay, so now we start our computations. I will start with the surface integral, the curve integral. So for the curve integral, what is my curve? My curve is exactly this curve. It is the boundary of the circle, which is x squared plus y squared equals 1. This is the x, this is the y. Of course, we are dealing in R3, so the z coordinate will be 0. Now, your orientation, you need to look at this figure. Your orientation of the curve is running from the positive x-axis to the positive y-axis. So this is the positive x-axis, so this is the orientation, so it's counterclockwise. Now you say, okay, what is the parameterization as a curve? And remember, the parameterization for the curve is in t in terms of one variable. So remember, this curve is cosine t, sine t, and the z is 0. We need to compute r prime of t, which is negative sine t, cosine t 0. Of course, the t is between 0 and 2 pi. So now when you compute the integral, now we have standard computations from 0 to 2 pi. F, so you take the parameterization, plug it into f, dot r prime is this, dt, and you take the r, plug it into your f. So your f is 2x, y cube, and z, which is 0. So now if you compute this integral, it will be from 0 to 2 pi minus 2 sine t cosine t plus cosine t sine cube t dt, and nicely everything is 0. Remember we explained earlier these ideas about why these integrals are zeros. We can have more clarifications later, but in this example I don't want to focus on the computation side. I want you to focus on the orientation of the curve to understand Stokes theorem to avoid any kind of computations. Okay, so the integral over this curve is 0. Now so remember the question was about verifying Stokes theorem. So I want to show that the surface integral of the curl is really equal to that thing. So now you go to the curl of your function. So this is your function. So what is f? Remember, f is 2x y cube z. You ask about the curl of f. So in this example, if you compute the curl, remember the curl is nabla across f, which is I, j, k. The nabla is this, and the f is this. And clearly, we went all the way to the first page in these notes. Going back. Okay, we are close. So yes, here's our computations. Okay, so if you compute this, it will be the vector 0. So basically the curl is 0. That means now, so if you want to compute the surface integral of curl f dot m dA, it will be 0 right away. So this is how we verify Stokes theorem, and this is the correctness of Stokes theorem. So in this example, imagine the question wasn't about verification of Stokes theorem. The question was, let's say, compute this quantity. Notice that in computations of this quantity, we needed to have a parameterization. We needed to do an integral. And in this example, it was, let's say, straightforward that the integral is 0. But in some other examples, it's not necessarily that easy. So in this example, it would be much easier to do this integral. So instead of doing the curve integral and doing all the computations, in this particular example, it was much easier for us to compute the surface integral of the curl. And once you compute the curl and you find it 0, then you say, okay, there is no need to compute or to do any parameterizations or integrals, and the integral is 0 right away. So this is somehow a good application of Stokes theorem. Before seeing more examples,